recording. And I guess if Ian is ready, then he can get started when he's good.
Hi, everyone. Can you let me share my screen?
Sure, 1 second. All right, you should be a co-host now.
Okay.
So we're going over the 2016, sorry?
Yeah, so right now is final exam of for 2016. So first, I will go through the problem number 1. It's an open problem and it should be very simple. The first part is assuming the open is ideal. Whenever you see the open is ideal, you have to you can assume that the gain is infinite, then input resistance is infinite, and RL is 0. So it's very so first thing we need to find the voltage on the plus V plus and V minus, because as we mentioned before, the Rin is infinite, so the current flow into the open is also 0. So the V plus here is 0 volt, and because the open has infinite gain, so we can have the virtual short between the positive terminal and negative terminal. So the V negative is also 0 volt. So the next step, we can calculate the current flow from the voltage source through the R2 C1 and go back to the open. The current here is equal to Vs over R2. Therefore, the Vout is equal to 0 minus I times the impedance of the C1, because the voltage here is 0. So the current flows through the capacitance generate IR drop of I times 1 over SC1. So the transfer function should be very simple. It equals to minus 1 over SR2 and C1. For the second part, which is we can directly see from the transfer function, we can see there's a 1 pole at the origin, and there's no 0. And the third part is that when the input is a unit step function, and we want to check the output waveform. Here, because the open has a limited through rate of 1 volt over 1 microsecond. So the first step, we need to check whether the open is in through rate region. So we can assume that open works as ideal. So when there is a step from 0 to 1, the current flow through the resistor is 1 volt over 1K, which is 1 milliamp. Assume the virtual graph still holds, and assume there's no through rate issue, we can see that the current charge the capacitance equals to minus C2 dVr dt. So we can see the output voltage change will be 1 milliamp over 100 picofarad, which is 10 volt over per microsecond. Apparently, because right now the open through rate is limited by 1 volt per microsecond, so our open right now is already into the through rate region. So since the open is going to the through rate region, so the maximum output voltage change is equal to through rate, which is minus 1 per microsecond. So as we can see that when the input apply a unit step response from 0 to 1, and the output, because the maximum voltage range change is only 1 volt per microsecond, so it just linearly decrease its voltage and touch minus 1 volt at 1 microsecond. It is also worth to know that in through rate, there's no virtual short anymore, because right now your open is non-ideal. So although in this problem we don't ask you to calculate the V minus, I think it is also instructive to serve as practice to draw the V minus here. So because the dVr dt equals to slew rate, which is minus 1 volt per microsecond, so we can calculate the current flow through the flow through the open under the slew rate condition, which means that the current right now is equal to 0.1 milliamp. And it means that the current here is 0.1 milliamp. It means that the V minus is equal to 0.9 volt. So just as we mentioned before, there's no virtual short. So even V plus is 0 volt, V minus right now is 0.9 volt. It's not 0 volt anymore. And the fourth part is
Hey, Ian.
hi.
Could you go a little bit more slowly? It seems that some of the students are having trouble keeping up.
Okay. So is there any questions so far?
Yeah, please ask questions as we go along. This is not helpful unless you're learning.
It's mainly just that, like, I haven't worked through this problem, so just looking through the solutions, like, if I had worked through this problem, it would have been more useful. That's why I wasn't sure if, like, were we expected to work through this problem, or like all the problems. I only worked through like the 2018 midterm or final.
I think just because of time constraints, we won't necessarily be able to go slow enough such that if you haven't worked through it before, it'll be like immediately clear what's going on. But the hope is that if you're able to work through this beforehand, this should be mostly straightforward, or at least, you know, this should clear up stuff as we go along. But otherwise, this should also, like, I guess, prepare you mentally for when you do try it. So yeah, that's just like a time constraint thing. So sorry about that, but we'll do our best. If you have questions, please let us know as we go along.
Sure.
One question about the op-amp setup at the top. Why doesn't the current go through RL?
Oh, yeah. Yeah, the current will go through RL, but because the output impedance is 0, so actually we don't need to care about RL.
So it's like an ideal op-amp sort of situation?
Yeah, because in this question, it still assume an ideal op-amp, except for one non-ideality is the slew rate is limited. So it still have infinite gain, infinite input resistance, and 0 output resistance.
Okay, thank you.
Yeah. So any other questions? Okay, so let's move to the fourth part. So right now, we adding another non-ideality to the open, which means our open, the DC is still infinite gain, but it has limited frequency response. So in order to derive the transfer function, we should go back to the node analysis. So because in the open, V out is equal to the gain times V plus minus V minus, right? So, and here our Rin is still infinite. So we can see that just as we do at part A, the current flow through the positive polarity is still 0. So V plus is 0 here. So because V plus is 0, so we can see that V minus equals to minus V out over VA. So when we plug this voltage into the equation, the current flow through the resistor and the capacitor equals to Vs minus V over A over R2, and plus V out minus V out over A over 1 over S2 is equal to 0. So when you solve the algebraic equation, you can get a transfer function like this. So as you can see, there's a pole at 0 and a pole at 1 plus omega u R2C2 over R2C2, because typically we will design our op-amp to have very wide unity gain frequency. So we can, this term can be approximately to minus omega u. And for part E, it's very simple when we need to consider another non-ideal effect of the non-zero input bias current. So here, because the output voltage is still V plus minus V minus times A, when there is a current flow into the op-amp, because there's a external, there's a resistance external, so it will generate a voltage drop at a V minus and V plus terminal. So as we can see, V plus equals to the IB minus IB times Rx. And for the V minus, it equals to minus IB times R2. So we calculate, it will corresponding to the V out of AIB times R2 minus Rx. So in order to null out the DC offset voltage, we can choose the R2 equals to Rx. In this way, the output offset will become to 0. So is there any other questions so far? Okay, so let's move to the next question.
Okay, so that should be number 2, which I think Alex is doing.
Give me a second. I'm trying to pull up the. Can you let me share the screen?
Done. Should work now.
Okay, so so we first identify what the core circuit is, and that should help you figure out what all these other parts are doing. So this is going to be the main circuit, and these are just going to be current mirrors everywhere. We know that this is like 10 times the size of this guy. This is 5 times the size of the original, current reference. So then the current through this is going to be 250 microamps, and this is going to be equal to 500 microamps. So we've already defined all the currents. Now we need to talk about the voltages. So let's just call this V1, we can call this V2, we can call this V3, V4, V5, and then V6. Okay, so we use the equation for current. So we know that ID is equal to 1/2 mu(n) Cox VOV squared, and then we have the W over L. Usually put it in the front. You do some math and you get that V1 is equal to 1.5. So this is, you equate, there are values for everything in here, and I'm solving for V1 first. So I have 50 microamps. This is 100 microamps per volt squared. VTH is equal to 0.5, and this is equal to 1. And so then V1 is equal to 1.5 volts. And so we notice that V2 is under or that this transistor on top also needs to have the same voltage in order to sustain 50 microamps. And for that reason, so sorry, we don't need to draw V3 there. V3 and V1 are equal, so it's redundant. V2 is going to be equal to 3 volts because it needs to have 1.5 volts right here for VGS in order to sustain the current. And then we're going to have a very similar situation for V6, where we need to have a VGS that's equal to 1.5 volts. But in this situation, V6 is going to equal to 5 volts minus 1.5 volts. So then we get 3.5 volts. And then the interesting part is that V4 is going to equal 1.5 volts. And the reason for that is because we also need a plus minus 1.5 volts on here. And yeah, so we have V6, V4, V2, and V1. We're only missing V5. And this one's kind of tricky because we've already defined V4 to be 1.5 volts. And so then we know that this transistor and this transistor are like almost identical, and they're running the same amount of current. And so V5 is not clearly defined, and usually if you don't know if it's clearly defined, you usually use the sizing to get an estimate of how much of what the voltage is at V5. So I would, since these two devices are identical and they're, they have the same mu and Cox, they have the same width and length, they have the same current. So then I think it's reasonable to assume that V5 is going to be the division of 1.5 and 5 volts. So then you're just going to get 5 volts minus 1.5 divided by 2, which is 3.25 volts. Okay, so that's part A, and then we want to find the signal path. So I'll just draw it up here. So the signal path is pretty clear. It's from VS all the way to VO. So we have a signal path. Now we should redraw the circuit. As we mentioned in the first part, we know that this is the main block. These are just biasing sections. Yeah. So when you redraw this circuit, it's going to look a little something like this. It specifies not to draw the small signal model. It's not entirely clear what they were going for with like redrawing this, but not including this small, or not drawing it as a small signal model. So I just replaced the current mirrors as like these voltage sources that are going to force the current to be here, to be whatever it was over here, some ratio. Another way that you can draw this would be if you're assuming that you're in small signal, you can replace everything with, shorts for the biases. And then we'll also have this is for small signal. Biasing from current mirror. So then we have this capacitance. This is C infinite. And we have this RS, and we have this V signal. Okay. This is ground. Okay. Now when we draw the small signal model, we replace this. So one note to make about this capacitor, treat it as short. So we're actually going to ignore that in a second. So this goes away because this is grounded. This is also grounded, but fortunately we still have this node. So then this stays. And then we have this guy over here. And this guy goes away. So then we're only left with an ROP looking up and yeah. Okay, so that's drawing that. So now to calculate the voltage gain, I'm going to use the approximation that GMRO is much, much bigger than 1. And I'm just going to calculate some of the values that I want at the moment. So GM is 2ID over VOV. VOV is equal to 1.5 volts minus 0.5 volts, which is equal to 1 volt. ID is 250 microamps, and this results in 500 microsiemen. RO is equal to 1 over lambda ID, so they have 1 over 0.05 times 250 microamps, which is equal to 80 kilo ohms. So then when we, this is just to have it in mind. So now when we calculate the gain of this, I'm going to actually divide this up into blocks. So I'm going to calculate the transfer function into here. So I'm going to call this the actual VI, or, you know. So I'm going to redraw this circuit. So so first thing is going to find VS, VI over VS. And looking up on this circuit, this is sort of how it simplifies down to. This is VI. So this becomes simply a voltage divider. But since I'm using the approximation here, I am going to ignore RO3 and simply use 1 over GM4 over RS plus 1 over GM4, which comes down to 1 over GM4 RS plus 1, which is 1 over 3. So this is what VI over VS is equal to. Now we need to find VO over VI, which if you look at this, we just look at this guy. We know that this is if we connect a short here and calculate the GM, we know that the GM is going to be source to generated. So when we have source to generated, our big GM is going to be equal to GM4, 1 plus GM4, and RO4 or RO3, because RO3 is what is causing the source degeneration to our GM. Okay, so we have that. And now we need to calculate the output impedance. So the output impedance, looking into here, this is our VO, we're going to see ROP5 looking up, and then we're going to see looking down is going to be approximately GM4, RO4, RO3. So then that's kind of what ends up happening. So RO5, GM4, RO4, RO3. So from this, we can tell that GM4, RO4, RO3 is going to be much, much bigger than RO5. And for that reason, we can approximate RO out to be RO5. Another thing to keep in mind is that RO5 is equal to RO3. And so then when you calculate the gain, you're going to get GM4 RO. I'm just going to call this RO now because it's pretty much the same thing. You're going to get this comes out to 40 or something like that. Let me just double check my notes. Yeah, this is like 40, the GM RO. And so this comes out to 40 over like 41, which is approximately 1. So then to get the total gain VO, VI times VI over VS is approximately 1 over 3. Okay. So now we need to include all the capacitances in this circuit, which is not easy to approach. If you look at it, it might look intimidating, but once you start breaking it down, it actually turns out that it's not that bad. So we have to include all the capacitances for all the transistors. So, why am I drawing that? 5. So I'm just going to ignore CGS5 and CGS3 ignored because connected to ground. So the gate and the source are connected to ground, so it's just going to ignore CGS for 5 and 3. So now we just need to take into account the part CGD. So this is CGD of 5, and this is CGD of 4. Okay, so then now we have 2 time constants. We're going to have one here, and then we're going to have another one here. So let's calculate the time constant for the first one. It's going to be CGS 4 plus CGD3 times some R equivalent at 1. Time constant 2 is going to be CGD5 plus CGD4 times some equivalent. So for T2, we're going to use this as RO5 and R equivalent 1. We're going to use looking up is going to be 1 over GM4, which we're going to say is much, much smaller than RO3. Give me a second while I take into account RS. So then we should have 1 over GM4 in parallel with RS. I think that is correct. Yeah, we have to keep this in, we have to take into account RS because they're both about the same quantity. All right, so then T2 is equal to about 8 nanoseconds. And then T1 is about equal to, I have to, and this T1 is about 333 picoseconds. So as you can tell, T2 is the dominant one. And so when you calculate your F3 dB, you get approximately 19 megahertz. Okay. I think that's it, Aviro.
Okay, sure. So unless anyone has any questions about that last problem, then I can get started with my yogurt container and we can go and look at number 3. There's a question in the chat, Alex.
Why don't you consider RO4 in the calculation of the second time constant? I think it was the approximation. When you look up into a transistor, you use the 1 over GM4 approximation. And I stated the approximation on the top where it's like GM RO is much, much bigger than 1. The full equation for looking up into the source of a transistor, I think I have it somewhere. It's like, I think it's like GM, 1 over GM in parallel with something.
Okay, are we ready for the yogurt container experience? Oh, yes.
Oh yeah.
We are ready. Cool. Okay, let me. Okay, so I don't have a printout of the exam with me at the moment, so you'll just have to follow along on your own. Maybe pull up the exam on the side. I'll do my best to kind of describe what the gist of each subpart is. So, but even then, if something doesn't make sense, just make sure to ask me. So, yeah, this is a junction field effect transistor. In this class, we studied MOS, metal oxide semiconductor field effect transistors. So we get to see how this actually operates as a transistor in this great, final problem where you are learning stuff as you go along. We love that. So part A of this problem is more or less supposed to be just kind of a warm-up. So here we're asking if we just suppose that the semiconductor bar in the middle of the structure is not actually p-type but is intrinsic silicon, then what would the resistance of the structure be? And so in order to do that, we need to find the resistivity, and we also need the dimensions. Luckily, I think all of the dimensions are given in this problem, so it's more or less just a plug and chug formulaic kind of thing, but you have to make sure that you get the values that you're using correct. So the first thing to note is that the concentrations of the holes and electrons will just be the intrinsic values given in the front matter of this exam. So these are the intrinsic concentrations. And then with that, we can look. So what the one approximation that we'll make in addition to this is that when we look at the doping curve, mobility curve of these devices, of silicon, I guess, they're going to look kind of like this, and this is given in the front matter. But we're just going to take the values of the mobility at these 2 points, which are the lowest doping, to be the values of the mobility that we're going to be seeing with intrinsic silicon. So these values are around 500 centimeters squared over volts times second, and that's for holes. And for electrons, we have about 1400 centimeters squared per volt times second. And so with that, I think we have everything we need to find the conductivity. So that's going to be Q times mu n times n plus mu p times p. And we've already shown that we know what n and p are for intrinsic silicon. We found the mu values, and we know that Q is going to be 1.602 times 10 to the negative 19th coulombs. And with that, we can calculate the conductivity, which I think will come out to around, this will come out to around 9.3 times 10 to the negative 6th. Let's see, it'll be 1 over ohms times coulombs, or not coulombs, but centimeters, I think, if the units are correct. Let's see. Yeah, I think that's good. And then with this value of the conductivity, we can find the resistance, which is rho L over T times W, and rho is just equal to 1 over sigma. So this is going to be L over T times W times sigma, which will come out to around 2.3 mega ohms at the very end. Okay, any questions about that? Too easy? Okay, cool. Moving on. So part B, this part, the question wording is, if we want to actually dope the body is the semiconductor slab in the middle. If you want to dope that to be p-type instead of intrinsic silicon, should we add a group 3 or group 5 element? And this is a very straightforward. I guess you can either memorize this or you can remember how doping works. And so group 3 means that we have 3 valence electrons. So silicon has 4 valence electrons. And if we add if we add a group 3 atom to silicon structure, what is happening is that we're actually taking away a valence electron from silicon and we're generating a hole. So you should always associate group 3 with hole generation. Well, that's a tricky term because we have actual generation processes, but holes are created, and that's what we want in this case because it's p-type. So we need group 3, and that means we need acceptor atoms, e.g. like boron or something. Boron is one of them. And yeah, as a result of that doping, we're going to have some Na. This is the doping. And then eventually the concentration of free holes will just be approximately that value. Any questions about that? Okay, once again, fairly straightforward, but there are places you can get tripped up, so keep your feet, I guess. So, right, part C, next part. So for part C, what we're doing now is we're going to say that Na is going to be 10 to the 18th per centimeter cubed. And so that will cause P to be that value now, just by the work that we did in part B. So with that, now we can calculate a different value for the conductivity essentially. And most of the rest of the problem is the same as what we did in part A. So yeah, with this fact, we can say that the concentration of electrons is going to be Ni squared over P by the mass action law, which is 10 to the 20th over 10 to the 18th, is going to be 10 squared per centimeter cubed. And the conductivity equation is the exact same as it was before. So we have mu n times n plus mu p times p. And this is approximately equal to q times mu p times p, just because this p term is 10 to the 18th and this n term is 10 to the 2. So if these mu terms are around the same, which to an order of magnitude they are, then this term is going to definitely dominate. So we can look at the same mobility curve that I was referencing for part A, and we'll see that added doping of Na plus Nd equals 10 to the 18th centimeters per centimeter cubed. Then we get that mu p is going to be equal to, I think, 160 centimeters squared per volts times second. So with that, we can once again calculate the conductivity. We get that it's around 25.6 this unit. And then we can plug it into the resistor equation, which is this L over TW sigma. And we'll get that this is about 0.39 ohms. Any questions about what I did there? No? Okay. Right. So part D is when we kind of get into conceptual problems, which can be tricky if you've never seen this kind of problem before. So here what we're asking is that, let's see, we're asking that if we bias the gates, so there are two gates in the JFET structure. If we bias the gates to be a positive voltage, what's going to happen to this structure? And then we're going to assume that the drain and the source are grounded. So I'll draw this up. We have our body in the middle. We have one gate. We have another gate. And then we have our, I think this one is the source, and this one is the drain. So we're going to ground these two. But we're going to apply some positive voltage over here, V plus. And we want to see what's going to happen in this structure. And so more or less, this is kind of just testing if you understand how p-n junctions work, and how this is a p-n junction and what type of p-n junction this is. So one bit of information that's useful from the first part of this problem is that these n gates are heavily doped to 10 to the 20th per centimeter cubed. And so that's 2 orders of magnitude greater than the p doping. And so what we expect to happen is that, certainly these are p-n junctions, so they're going to have a depletion region on either side of the gate in the body. But because the body is so much more lightly doped than the gate, then most of the depletion region will actually fall across the body. So what we're really going to see is that very little of this depletion is going to happen inside the gate, so we can just like basically ignore it. And more or less we have this relatively large depletion region within the body. And so we have depletion region and this actually this lowers the effective thickness of the body / channel. We'll call it the channel now because it's conducting charge. It'll lower the effective thickness of the body. So, effectively what we're going to see is that we have this new T prime here, and this is going to be the new slab of semiconductor that is going to give resistance to our structure, because this is where the current flow will happen, as opposed to in the depletion region where there are not sufficient charge carriers to sustain active current flow. Okay. Any questions about what I did in part D? Okay. Cool. Moving on, we have part E next. So now what we're going to do is we're going to set the gate bias to be 0.5 volts. And so we already said what we expected for a positive gate bias. We expect there to be a slightly increased depletion region on either side of the body as a result of this increasing gate bias, because this is, one thing to note is that with the positive bias, this is actually reverse biased. So reverse bias with VG greater than 0, and as a result, depletion region grows. Maybe, I'm not sure if that was probably the last question. Yeah, that is. So depletion region grows. Okay, so now this is more or less kind of a plug and chug of what happens when we change the applied bias from the, I guess, static 0 volts. So once again, we'll use the sigma is 25.6 this unit. You could say Siemens per centimeter, because the doping has not changed, so the conductivity will be the same where it's conducting. As I've just noted, we're going to have these 2 depletion regions on the top and bottom. So the effective thickness is going to be the original thickness minus 2 times the depletion width. As we calculate it for either this side or that side, it'll be the same, just because the bias is the same. And so we can make use of a one-sided junction approximation to find the depletion width on either of the sides. So this is going to be 2 times epsilon s, which is silicon, times phi bi plus the applied voltage over Q times Na. We've said that Na is going to be 10 to the 18th per centimeter cubed. Q we know. Epsilon s is given in the front matter of the exam. Phi bi, we'll get to that. Va is going to be 0.5 volts, just because this is a reverse bias. So as a quick sanity check, sometimes the signs of these don't go well. You should expect that the depletion width will increase when we apply a reverse bias. So in this case, with a positive VA, then X dep will be increasing. So it makes sense for this to be a plus as opposed to a minus. So, sometimes the terminology can be confusing, but that's the way to check yourself. And yeah, getting back to phi bi, we have that equation for it, nifty kt over q times natural log of na nd over ni squared. So you can either, do the natural log out. I think you're allowed calculators, or you can use an additional approximation that says that this is equal to 60 millivolts times the base 10 logarithm of Na times Nd over Ni squared, which should fall out quite nicely just because everything is provided in terms of exponents of 10. So Na is going to be 10 to the 18th, Nd is 10 to the 20th, because that's the gate. Ni squared is 10 to the 20th, and then this should be a fairly straightforward multiplication after that. So I could go through all the rigmarole, but eventually we get that RDS is about, RDS, which is the same resistance of the structure that we were finding before, is now about 0.394 ohms, which is slightly more than it was before, which would make sense because the effective thickness has decreased, so it should be more resistive. And so as a result, the resulting IDS from this resistance is going to be IDS is equal to VDS over RDS. And we'll see that this has actually decreased. So we're going to elaborate on this in the next part, but we have what is actually a variable resistor structure, which is a lot like the variable resistor that a MOSFET can produce. So, ooh, that's very cool. This can almost be a transistor. And so that's kind of what the motivation in part F is. So let's see. So explain how the structure acts like a transistor. Does the current increase or decrease with increasing gate bias? Explain how the gate controls the channel. So when you increase the gate bias, this leads to the depletion regions growing, as we saw. So the current from the drain of the source decreases. And so this leads to the gate controlling the channel conductivity like a MOSFET in triode, as I mentioned. Very cool. If we want it to act, so this is, currently this is like a voltage controlled resistor. If we want it to act like a complete transistor, the current must eventually saturate at some point. Otherwise, we won't be able to use it in steady state currents or steady state circuits. So to be a transistor, current must saturate. See next part, because that's the question of the next part. So now we're going to ask, if we bias the drain voltage to some high negative value, what happens to the device? So before, in part C, I'll just pull that back. In part C, we had these depletion regions here, and they're more or less kind of uniform across the length of the device. What happens when we change the voltage that we apply to the drain is that we actually see more depletion because there's more reverse bias in this direction than we see over here. So what we end up getting is that in this sandwich structure, the depletion regions look more like this, kind of like a triangle shape. So this is the channel, and what happens is that towards the edge, towards the drain edge, we get a possibly pinched off condition. So this is different from the pinch off that we see in a MOSFET, but the essential takeaway here is that the channel will be restricted to the point that current will no longer flow. So we saw that VGS is the knob to turn to set the conductivity of the channel. Or, you know, this is, or conductance, set the conductance of the channel. And now BDS is the knob to turn to set on level of the channel. And so this is a transistor now. This is exactly how our BJT, or this is, you know, exactly how our BJTs, how our MOSFETs work. These are the knobs that we turn, and this turns the knobs in the same way, or in a different way actually, but in the way that we expect at a larger, higher level. Okay, so now in part H, we want to identify the physical origin of the capacitors in the structure. So this is kind of a long problem. So we're going to draw the sandwich again. And very quickly, we're going to note that I think the assumption is that we still have some VD being applied. So the depletion regions are a bit imbalanced, but essentially we still, you know, the causes of the capacitances in every case are going to be the depletion regions. So we have one here and we have one there. So CGS is just going to be if we call each of these CDEP S and CDEP D, CGS is going to be 2 CDEP S, and CGD is going to be 2 CDEP D. Both of them are depletion capacitances. Okay, so there are a few questions in the chat. I don't know those from before. Okay, but does anyone have a question about what I've done thus far? No? Okay, cool. So those are the capacitances in this structure. And finally, we are going to draw a small signal model. And the wording of this question implies that I don't have to do too much calculation, so I'm not going to do too much calculation. But essentially, this is the same transistor small signal model that we've seen for MOSFETs and for BJTs. So we have this GM, BGS. We have an RO. This is the source. This is the gate. This is the drain. And this is CGS as we calculated it above. And this is CGD as we calculated it above. And so just to kind of write a fully correct expression, I think that we can say that CDEP in either case is approximately equal to W times L times epsilon S over the depletion width, which is dependent on, this is dependent on position, or, you know, dependent on source versus drain. And so that's kind of, this is kind of where this problem fell apart, because it's kind of too tough for students to determine that one. But GM is going to be partial IDS over partial BGS at the VD of interest. And RO is going to be partial IDS over partial, you know, actually this is 1 over RO, partial VDS at the VG of interest. And yeah, you could make the approximation that this depletion capacitance is maybe like 2/3 times W times L times epsilon S over X step. But this is a MOSFET specific approximation. So it doesn't necessarily hold here. But you know, if you wanted to actually apply some MOSFET stuff here, then this would be the place to try, I guess. But yeah, that's a small signal model. The point of this problem wasn't to really get into the nitty gritty of what's happening in terms of equations, but more or less to show that transistors are transistors, and the device physics stuff that we model in this class actually does apply here. So if we don't have any questions about that, then I guess I'll move back to having Alex speak about number 4 from spring 2018, and then I'll fill in at the end once again.
All right. So we're doing question 4. This is standard NMOS. So what are some choices for the dopants Na? Yeah, so we want to have acceptors and we have a choice between group 3 versus group 5. And if you're like me and you didn't remember which ones are the acceptors, I use the number 3, and you want 4, so then it's lacking 1. So this is how I figure out that this is an acceptor, and so you want a group 3 element. So that's the answer for group part for that part. And then here's just some like boron and aluminum, whatever, aluminum. Yeah, so that's pretty much the answer for that one. What are some appropriate values for the body of the device? So there is one thing that you want to be concerned about when we're talking about the body, and it has to do with this parasitic diode that you have here. You want to make sure BB is most negative. Vice versa for the PMOS. And that's just because you don't want this to be forward biased. So that's kind of, but you can pretty much have any body biasing as long as you don't break this condition, or rather I should say, you can put any body voltage that you want and not have this be forward biased. But if you do have the body bias, then you're going to run into problems like the second order body effect, where your threshold is changing its value. So I don't think they're asking about this in the question, but it's something to just keep in mind. I think in the question they're more concerned about making sure that your body bias is less than any other voltage so that you don't forward bias anything. And that's pretty much it. I think that's what the question was looking for. But I think another thing to consider when you're designing stuff is in the small signal regime, you don't want this body effect to affect you. Yep. Okay. And in this situation, since the gate and the body are equal, then the flat band voltage is going to be equal to 0. And then looking at part D, this is a kind of like a MOSCAP where you start to attract, you're going to have carriers here, and then you're also going to start having these ionized dopants. And that's pretty much it. That's pretty much what's going to happen there, since you're below the threshold. And you just draw the little depletion region. Do you want to continue?
Yeah. So you have a few you have depletion region around the source and drain as well, as an additional note. Yeah, so this is similar to the previous problem in the sense that those are heavily doped with respect to the body. So most of the depletion happens in the body as opposed to in the source and drain implants. Yeah. Okay, so do we have any questions about the first part of this problem? No? Okay, if we're good, then we're going to return back to my yogurt container and we can work through the rest of this problem. So, okay, so hopefully you can follow along with this problem if you have the PDF open or something. Sorry about that once again. But part E is asking if you give VG less than the threshold voltage, what is the surface potential of this device? So you can assume that body, source, and drain are all grounded. And with these conditions, all that we need to find is that VG is going to be these two voltages, the voltage across the depletion region and the voltage across the oxide added together. So this, and the term that, so Vox is going to be the charge at its surface over its capacitance. So the thing to note is that at this point, the charge at its surface is just going to be from depletion because we don't have inversion yet. VG is less than VT. So this is the charge at the surface. And in addition, we have some VDEP. And the thing to note here is that VDEP is actually going to be equal to the surface potential. This is the surface potential, and that's what we're trying to find here. So this is the unknown. So we can express QDEP as this expression, so 2Q epsilon S NA times VDEP, and we've just noted that VDEP is going to be phi S as well. So we're going to be 2Q epsilon S NA times phi S. And with that, we can plug in some stuff, and we're given VG. So we can arrive at a final equation of VG is equal to this QDEP, 2Q epsilon S NA phi S over Cox plus phi S itself. And so now we have an equation with one unknown and a bunch of knowns. So this is known, 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 and all that's remaining is this, and we can solve for this. We can now solve for phi S, which is what we wanted. So that was that problem. It's a bit intimidating at first, but all you need to use is this, I guess, Kirchhoff voltage law, adding voltages together to find adding unknown voltages together to sum to a known voltage, and then we use what we do know to substitute in and find or identify the unknown. Any questions about what I did there? No. I'm showing only a bit of it. No? Okay, cool. So with that part out of the way, we can move on to part F. Part F of this is, so we now give VG is equal to the threshold voltage. So this is at the onset of inversion. And we measure the electric field in the oxide as EOX, and we measure the electric field at the surface as ES. And so now we're going to slightly increase VG to be VT plus V star, where this is some positive voltage. And so now we want to see, how do EOX and ES change? So, the main takeaway here is that ES will not be changing appreciably, since all additional charge comes from the inversion layer. So if we remember our like QV curve from our MOSCAP module, this is an NMOS structure. We have something that looks kind of more or less like this, VT. And so this, the change in charge here for a very so what's happening in this structure is that as we scale in the VG here, we have what is actually just a capacitance of the oxide determining the charge. So the differential charge here physically does not come from the inversion charge. It comes more from the charge that is collecting at the gate of the oxide. So yeah, and so gate of the oxide as well as the surface. So this additional charge, this inversion layer, is at the surface. So as a result, we see most of V star dropped across the oxide, Vox. And so as a result, we can express the change in the oxide field as the change in Vox over the thickness of the oxide, which is going to be V star over Tox. And that's what we're going for here. So you can tell here from this QV curve that, or I mean, you should, I guess, know this to draw the QV curve, but because this is a linear capacitor, because inversion is happening at the surface of the oxide, all of the voltage will be dropped across the oxide as opposed to across the depletion region. So I think that was kind of confusing, or kind of non-intuitive. So do we have any questions about that? No? Okay, if we're good with that, then we will move on to the last part of this problem, which was a real gut punch when I did this final. So part G. So now we're going to do the whole derivation. Woo. That's a question, and I guess they were kind enough to provide the actual final solution. So 2 pi p plus 1 over Cox square root of 2q on S NA -2 phi p. So let's just break it down step by step. So at the threshold of inversion, we have the surface potential phi s going from phi p, which is in body, to negative phi p. And this is where our inverted carriers come from. Or this isn't actually where they come from, but this is the rationale behind why they can exist there. And so in order for that to happen, well, so let's see. So I'll just, so the expression for phi s actually, so this is the surface potential. The expression for phi s becomes, or I guess this is psi s or whatever, but I just write them as the same. This becomes -2 times phi p, and so that represents the inversion from phi p to negative phi p at the surface. And so we can say, using the work that we did in the last part, that Vg is equal to Vox plus, this is actually psi s, but I'm just gonna, I can't differentiate between Greek letters, so it's going to be phi s and psi s at the same time. So this is what we solved by a KVL in the last part. So let's see. Looking at my notes. So in order to zero out the built-in potential of the structure, and built-in depletion charge, we have two other terms. So the built-in potential structure, but built-in potential of the structure is where the flat band voltage comes from. So that's just the arbitrary voltage that we need in order to flatten the bands, as they say in device physics terminology. And then the depletion charge just kind of has its, charge over Cox is going to be the voltage needed to account for that. So this is going to be Q depletion, which is that charge over the capacitance, which is Cox. And so the final expression is that Vg, which is going to be equal to Vt in this case, is going to be VFB plus psi s or phi s or whichever one it is, plus this Q dep, which we saw before, is going to be 2Q epsilon s Na times psi s over Cox. And we've shown, or we showed, that psi s has to be -2 phi p in order for inversion to happen. So we can just plug that in here and here for inversion. And that is the entire derivation done from start to finish, more or less. So I think that's it for what we wanted to cover in this review session. In the last 2 minutes, you can ask me any questions that you have about this or any of the other problems. Otherwise, good luck with your studying, and we will announce how to get the actual solutions sometime later. So thank you.
Just a logistic question. Is the midterm still going to be mostly post-midterm? I mean, sorry, is the final going to be mostly post-midterm material, or is it sort of like this review session?
So all of the stuff that we did in the review session is in scope. So don't forget the stuff from before the midterm, but necessarily the content from after the midterm hasn't been tested yet. So we need to give it a fair shake, or you need to have a fair chance to demonstrate that you understand it. So from that perspective, it will be mostly material from after the midterm, but you shouldn't be surprised if content that is kind of integrative of all the material in the course shows up in the final. So like you should know the stuff from before the midterm. The final is definitely cumulative, but the focus is on stuff from after the midterm. Yeah.
Right. Okay. Thank you.
Any other questions? Okay, well, good luck studying and thank you for coming. Goodbye.
Thank you.